This session going to be discuss about fundamental aspects of the memory. It is a part one of the memory model, the model 3 of computer organization. So the milestones are as follows. So fundamental aspects of the memory going to be discussed, and other aspects will be looking after this. So let me see. Fundamental component of the memory will going to be discussed, and the RAM and semiconductor random access memory and internal organization of the memory. The after discussing the internal organization as a small amount of memory, the huge amount of memory going to be discussed with the memory organization. And we have the cells called dynamic random access and static random access memories. So here you can observe the uh, maximum size of the main memory. What is the size memory going to be used here? So that may be several GBs or several MBs. Those memories are going to be fetch the data from the memory, either maybe byte addressable or word addressable, maybe little Indian or big Indian concept they are going to be followed to bring the data to the processor. So CPU main memory connection, there is a layout of the buses in the CPU. So there is a processor bus, they're basically faster, and memory bus, so there may be a little slow compared to the processor bus, because the electromechanical device will be connected, basically they are inherently slower because the mechanical component will be involved, so it may be a slower compared to the processor bus. Similarly, the other bus will be there, maybe PCI bus, memory controller bus, maybe DMA controller and SCSI bus, so on that. So the main connection between central processing unit and memory is a vital part of the central processing unit, where that buses will carry the information of data control and addresses. So to see this layout of the central processing unit, the processor will be there. So processor will be established, and it will produce some address through the MAR, that is called the other side we have memory, which will be receive the information from the processor, and it will try to search in a memory. After getting that data, it will send back to the processor. So from the processor side, there is two registers are involved to send a data, so address, and receive a data through the MDR, to send an address through MAR and receive a data through MDR. So these two binary registers are available in the CPU premises, especially the part of the processor. So the memory address register will release some address, that is a k-bit address, so from the processor, saying that, so we need to I need this data, you can bring that. So that address will be here, so that will be travel across the bus, so that is address bus, and reach to the memory. Once it reached the memory, so there will be a 2 power k addressable locations will be there. So the k bit address will be sent 2 power k. For example, 2 bit will be sent, that is a 2 power 2, that is a 4 address lines. Similarly, 2 power 10, that is a 1024 address locations. So like that, 2 power k, then word length will be n bit. So word length will be 2 bit is address, then 2 bit will be fetch. 8 bit will be address, and 8 bit data will be fetch. Similarly, 16 bit, 32 bit, 64 bit, so on, that go to the higher end machines, so it will fetch the larger word length of the instruction or data from the memory. So after receiving the data, so it will search the location in the memory, and it will be upload the data onto the data bus, so that is a n bit data bus, and it travel across the bus and reach to the processor premises. So the somewhere has to be welcome that, so that the person is responsible, that is a memory data register, is held responsible. He will welcome the data which is coming from that memory or other devices. So right now we are discussing or communicating the processor with the memory, so memory will be send address data. So there is a other additional control signals called read and write signals, and these control signals will be initiated by processor and reach to the memory, and other words also initiated from the memory and reach to the processor, so that read completion, write completion, and similarly memory function completion. So when you insert the data, I request some operations, so it will be fetched from that corresponding location of the memory. It needs spending some certain cycles, so it need extra machine cycles to fetch the data, because maybe data is available at the memory, so that we need an additional time for that. So after discussing these basic concepts, as you can see, the measures for the speed of the memory. The measures of the speed of the memory is the most important. So that may be the memory access time or memory cycle time. So memory access time, as the instructions are initiated by the processor, so that may be a load store instruction or memory related instructions. So in that case, the memory access time will be more. That more number of cycles are spending. That may be a fetch, maybe a execute, maybe write back result, and the store the result. So there are several phases will be look after that. Each phases will be required one clock cycle. Such there is some more than one clock cycle is essential to reach to the memory component and bring the data. And an important design issue is to provide a computer system with a large and fast memory as possible within a given cost target. So the faster the memory and cheaper the cost. Along with the faster, there should be large amount of memory. The more number of cells should be there, so we can fetch the data or store the data more in a single attempt. So the cost is a factor, and speed and large the amount of memory is also going to be a influencing factor in the most of the design issues. So most of the designer, so they will be look out for that. Several techniques to increase the effective size and speed of the memory. So there is a speed of the memory, as we discussed, that processor is having a registers, and those are basically flip-flops, and those are basically the inherently fast. So where other device may be memory is a mechanical device, electromechanical device, which may be inherently slow compared to the CPU registers. So that's why there is a mismatch between this processor and memory. So that mismatch we need to be that system designer should be adjust, so that can be possible through the help of the cache memory concept. So other one is a speed, the size we can the adjust with the help of the virtual memory concept. So speed gap between this processor and memory will be maintained or make up by the cache memory, and size size between this handling up amount will be because the processor handling in terms of the bytes, whereas the other device the memory will handle in terms of the blocks. So there is a gap between these sizes. So definitely that gap need to be make up with help of the virtual memory concept. So that we will going to be discussed in length in the subsequent discussion. So cache memory to increase the effective speed, virtual memory to increase the effective size. So those concepts will be most important as a part of the memory, especially in the computer organization. So coming to these aspects, we have seen the memory and the speed and address and data, and for which we have the CPU registers, general purpose registers, or MDR, MAR will be there. So that will be taken care to send the data. So coming to the internal organization of the memory, so here we can see that, so the memory structure we can see there is address, so address will be there, so there is 0 1 2 address will be there, so there is a 4-bit address, and data, that is a 4-bit data will be there in the memory. So the 0 located to the data 1010. So similarly 5101 is located to 001. So the data is a content of the memory, where address is the address of this memory. With help of this address, we can bring out or store some information into the data memory. So this is a memory structure. So let we see further. So the each memory cell can hold 1 bit information. So here we have 4 bit, 4 cells will be there. So like that. So eight rows are there, 4 columns are there. So 8 into 4, so 32 cells bit information will be possible to accommodate in this memory. So the memory cells are organized in the form of an array, right? So there is array, 0th array, 1 first array, similarly 5th and 6th, 7th array. So the arrays cells are organized in the arrays. So it is basically it is a matrix fashion. Memory will be organized in the matrix fashion. So you can fetch either through the row wise and column wise. So memory cells. So similarly, one row is a one memory word. So this is a one memory word. This is a 0th word and second word. Similarly, 7th word. So this is a one row is a complete one word. So of course here 4 bit will be there. Similarly, in the subsequent discussion, maybe 8 bit, 16 bit, 32 bit word may be possible, right? So all cells of row are connected to common lines known as a word lines. So cells row connected to word line and column connected to bit line. So row are connected to common line called word line, right? So word line is connected to the address decoder. So there is a for which we need to be uniquely identify this, we need a 3-bit. So 3-bit address will be there. So that we need to be fed into the decoder. There is a 3 to 8 decoder will be there. 8 output possible outputs are there. So that connected to the word line. So this discussion, there is a also additional circuit called sense and write circuit are connected to the data input output. So lines of the memory chip. So there is a sense and write circuit attached to the what we call it as the matrix. So that memory. So memory will be drive out the information or put the information through this additional circuit. So that can be happen, that is. So coming to the discussion of what we call it as a internal organization of the memory. So let me see small example of memory size 16 word into 8, right? So that is a 128 bit of memory possible to drive out. So organize here. So 16 words, that is 16 rows, 8 bit, that is 8 columns. So 16 into 8, 128 bit memory will be going to be organized here. So this internal component of the memory will look after. So the see that 16 words are there, for which we need a decoder. So that is a 4 to 16 decoder. 4 address lines are there, A0, A1, A2, A3. These are the address lines will be released by the CPU, saying that so the contents of the data of the memory location you please bring. So having received that address from the CPU, so it will be map onto the address that is a MAR. So that MAR will be sent to that through the address bus A0 to A3. So this address decoder will produce the output. So that is 16 outputs will be there. So that is 0 to word 15. So 16 words is going to be map are going to be identified in the memory. So from this end, from the other end, we can see typical memory cell. So this is a typical memory cell, square box, the rectangle box. So the memory cell will be, sir, one side is connected to what is a bit line B dash, and other line is connected to B. So these are the bit lines. So this is attached to, that is a one more rectangle shape, that is a sense or write circuit. This sense or write circuit will read information present at the cell, also it write some information into the cell, right? From the cell reading into the cell writing. So for which we have, there is a chip selection and read write signal. So what is a chip selection? So large amount of memory you can formulate with help of the small chips, because huge large chips may not available. So for which a large memory we want, we can construct with help of the small chips. So there is, in such case, huge memory you can going to be formulate. In that case, we need to be use several chips. So several chips involved in a big memory, then chip selection signal will be there for from processor it will release. And also want to read some information, there is a read control signal will be released from the processor. Also write control signal will be that write is a active low signal will be sent from the processor. From this will be bit b0 will be lsb bit of the data we may expect here, either input or output. So from this simple diagram we should be able to appreciate the single memory cell with help of flip-flop. So that flip-flop again will be made up with the transistors and diodes, capacitors, right? So the we have at a higher level you can see this will be look up to the look as a single memory cell, that is a flip-flop, right? Similarly the other memory cell we can observe. So like that the 16 memory cells we can organize here, 16 memory cell. So memory cell 0 2 so on, this is 15. So 16 memory cell organized for the bit 0. So at any given time from any one flip-flop or cell may be able to send or receive the data through to the real world, right? So this is a first column. Similarly the second column we can see. So these are the memory cells, and second column you can see that second column also 16 cells are there. Again separate right circuit will be there. From this we can expect b1. So similarly b1 b2 b3 so on up to b7, right? Because 8 bit is a output we are considering. So we have that is a data input and output b0 to b7. So that is a b7 bit. So b0 b1 b2 b3 b4 b5 b6 b7. So this is a b7, and word 0 to word 15. So this will be a complete 128 bits memory cell we can observe here, right? So I can observe this memory cell that will be going to be observed. So the entire memory component to with help of these 4 address lines and 8 bit data lines, and there is another pin will be required, ground supply and power ground and power supply. So and also chip selection read rate signal will be also there. So from this we can able to understand the how the memory organized for the smaller size. So let we see some bigger size or further smaller size. So earlier the 128 bit, now we have 32 bit. So that 8 rows and 4 columns. So 8 rows are there. So in each row will be 4 bit. So each row will be register 0. Then similarly last row will be last register, the register 7. So the 4 bit data word will be there, 4 bit. So for this address 8 registers we have 3 bit encoder, 3 input and 8 output will be there. So output will be generated, and 4 bit there is a write control will be there. So write control signal that is a read and write bar signal. So 32 bit we can observe that. So 3 bit per address, that is A0 A1 A2, 4 bit per data, that is a D0 D1 D2 D3 data, right? So 3 bit per address, 4 bit per data, and 2 bit for that is called 2 bit for what is called ground supply and power supply, ground and power supply. So ground and power supply. So altogether 9 pins will be we need to be established for the this 32-bit memory chip. Can observe here the memory chips are there. So this will be plugged onto the motherboard, where the slots are dedicated slots are there, as similar to uh, plug-in data card, memory card in a our mobile device. Similarly, we can plug in that so ICs here, so that will be have some size, maybe 1 GB or 10 GB, so on. That is, so that may be a typical example. Similarly, earlier discussion that 128-bit, so there was a 4 address lines are there, 8 data lines are there. So 2 pins for what is called ground and power supply. So altogether 14 pins will be there, right? So this is a 14 pins, so can essential to organize that 128-bit. Similarly, 1 kilobyte of memory we will discuss in the next slide. So that is a for 1 kilobyte, that is a 2 power 10. 2 power 10 is a 1 kilobyte, that is 1024. So plus 8-bit data and 2-bit ground supply, and altogether will be 20 pins. So this is 18 is wrong, so this is a total 20 pins will be essential to construct a 1 kilobyte of memory. So number of pin wise and size wise we have observed here. So there is a data size, memory size increases, pin size also going to be increased after certain memory size. The pin size going to be saturated or going to be minimum, because why we are freshing on the pins number of pins, because number of pins will be required more power supply. So more number of pins, then more supply is required. So and also more supply is given, that is a cooling is essential. We need to be cool that ICs, right? So that relatively depends on the size and number of pins, that is. So from this discussion, so we are able to construct the one more large memory. So that is a 1 kilobyte of memory. 1 kilobyte is a 1024. This 1024 locations, memory locations, we can easily identify with 2 power 10. 2 power 10. So 10 address lines is required. So 10 addresses, that is 2 power 10, 1024 unique locations going to be identified. So this 10-bit address we can split into, because memory will going to be organized in a matrix fashion. So in order to read out this matrix, we can go row wise and column wise. So row wise and column wise, this 10-bit address will be split into two components. One is a row address, right? So this is a 5-bit address will be splitted. So that is a 5-bit row address for row, and for which then also 5-bit for column address, right? So column address, that is a 5-bit column address will be there. So the total 10-bit will be divided into row address and column address. So having understood this, always need a decoder for this row address. So there is a 5 inputs will be there, and 2 for 5, that is a 32 output will be there. So that 32 rows will be uniquely identified from this decoder. So that is a word 0 to word 31, right? So similarly this 32 rows will be there and 32 columns will be there. Memory cell will be organized, and we have, so this 32 1K, we can also say 32 by 32, right? So 32 rows and 32 column is also going to be 1 kilobyte, that is 1024 bit memory. So there is a additional circuit we have keep discussed, that is sense or write circuit. So that will be trigger the memory cell, the store or bring out, right? So there is a data input and output will be there. So that will be a multiplexer 32 to 1. So because this is a 1K into 1, so there is a 1 output will be there, right? Similarly 1K into 8 is there, then 8 output we can expect. One input, 1 output, or you can use 1K into 8, so 8 input, 8 output. In that case 32 to 8 output multiplexer is essential. So here 1K into 8 memory organized with help of this. So I hope it is a crystal clear. Organization of 1K into one memory chip, that can be possible with help of the 10 address lines. So 10 address lines, there is a one data lines for this here. So 10 plus 1 and 2, one ground supply and ground and power supply. So 11 plus 2, 13 pins is required if you have one bit. Normally one bit or sometimes the 8 bit will be there. So then 10 plus 8 plus 2, so 20 pins will be required to organize a memory chip of 1K into 8, 1K into 8. So 1K into 1 is required, just 10 plus 1 plus what is 2, 13 pins is essential, right? So I hope it is a clear the concept of organization of 1K into 1 bit memory. So of course chip selection, read and write signal, the signals will be there. So having understood this, the memory of organization may be a small amount of memory. We discussed 32 bit, 128 bit and 1024 bit. Similarly, the huge amount of memory you can possible to construct. So in order to construct this memory, we need a different memory concept. So that is a philosophy. So that is a static random access memory and dynamic random access memory. So static random access memory consists of circuits that capable of retaining their information as long the power supply is there, right? So it will be constantly need to provide a power supply, so it will be maintain the data at the cell. So volatile memory, because their contents are lost when power supply is interrupted. So we have that the memory volatile, that is a fast access. So fast access, and that will be continuous power supply is required. The storage non-volatile, so that will be dynamic random access memory, large capacity, but it is slower, right? So let we see in detail. Access time of static random access memory are in the range of few nanoseconds, right? So few nanoseconds is essential to access this static memory. However, the cost is usually high in this case. So the density of the memory cells is lesser, so the cost may be increases. Inherently, the concept is like that. So comparatively, this static random access memory, we have the other alternative called dynamic random access memory. So dynamic random access memory is formed with help of the capacitors and transistors. So it will not retain the information indefinitely. So indefinitely. So contents must be periodically refreshed. So because the power supply is not there continuously, due to this data going to be loose. So we have to understand the philosophy of that dynamic random access memory cell. So based on that cell, the refreshing circuit is essential. Why need to be refreshed? The data may be loose. So in terms of some nanoseconds, after some nanosecond data going to be loose, before that nanoseconds of time, we need to be refreshed. We need to be refreshed in the sense we need to be supply power. So it will be regenerate and recollect that. So otherwise the data will be permanently lost. So that kind of concepts will be imposed in the construction of the dynamic random access memory cell. Contents may be refreshed while access them for reading. So static random access memory construction we can observe here. So there is a two transistors will be there. So their side is connected to called bit line, right? So there is a, you might be heard or seen that typical picture of the transistors in most of the computer, right? So that picture diagram, circuit diagram, and there is a NPN transistor, PNP transistors will be there. So those transistors we can observe. So we have that can be two transistors inverters are cross connected to implement a basic flip-flop. So that bit lines will be there. There is a two T1 and T2 transistors will be there, that is. So there is the transistor base will be connected to the word line, and the other will be connected to bit line. So the in between the transistor there is a NOT gate. The diodes will be constructed, the X and Y junction. So it will be have a converse value, that is, so cells is connected to one word line and 2 bit lines by transistors T1 and T2, right? So T1 and T2 transistors will be there to connected, that is. So we can have that. So when word line is at a ground level, when a word line word line is at a ground level, the transistor are turned off. uh, Transistor off when this is connected to ground line. Word line is connected to ground, so word line here connected to the ground, so then transistor will be off. The latch states retain its information. So information which is available at the cell which is locked, it retain means retain. When the word line connected to the ground, the information will be retained in the cell. So that is a static random access memory read operation. In order to read the data of this static random access cell, the line is activated. Word line is activated. So earlier to maintain the data it was ground. Now not activated. So line is to close to the switch T1 and T2. So T1 T2 are close. Then that word line will be become active. So earlier it was open, so that was a unlocked, that is. So sensor write circuit at the bottom monitor of the state B and B dash. So the B and B dash will be are the bit lines or connected for the columnly connected. So word line connected to the what is called uh, row fashion. Since a single DRAM cell uh, have only two components, transistor and capacitor, where we have seen in the previous that two transistors and diodes were there. Similarly, architecture of that DRAM cell, there is a one transistor and one capacitor. It can made in a high density and inexpensive compared to the other memory. It is a less cost compared to the static random access memory. So the capacitor connected to the ground. So the typical capacitor we have seen in the our motherboard or any electronic device. So these are the different type of capacitors. So normally exercise in most of the electronic circuits. So since amplifiers are disconnected, so disconnected when that is connected to ground, that is a capacitor, bit lines are pre-charged to exactly equal voltage that are between the high voltage and low, that is 0 and 1. So the word line is connected, so bit line is connected. So bit line are physically symmetrical to keep the capacity equal, and therefore at the time their voltage are equal, right? So bit lines are physically keep the capacitance equal, so therefore the voltage also equal. So presence and absence of the charge on the capacitor to store the data is important. So the presence of charge, it helps to maintain the data as long as the charges are there in a capacitor. So after certain amount of time, after certain millisecond or nanoseconds, so the charge is going to be loose from the capacitor. So this will be impact on the status of the memory, information of the memory. Memory is also going to be unable to hold the data, it is going to be loose. So for which we need to be refresh is essential. It is a refresh every few milliseconds, unlike random access memory we discussed in the previous, that is a static, which is refreshed only when the power is off. So only once that they need, but here required oftenly. Free charge circuit is switched off because of the bit lines are relatively long, right? So bit lines are long, they have enough capacitance to maintain the pre-charge voltage for a brief time. So the desired row word line is then driven uh, high to connected a cell storage capacitor to its a bit line, right? So word line then to connected to cell storage capacitor bit line. The transferring charge from storage cell to connected bit line or from the connected bit line to storage cell, right? So this can be happen transferring charges from the what is called the storage cell to bit line and vice versa. Since the capacitance of the bit line is typically much higher than the capacity of the storage cell, so this voltage on the bit line increases very slightly if the storage cell's capacitor is discharged, right? So discharge, that is, so the capacitor is discharged and decreases very slightly if the storage cell is charged. If the storage cell is charged, then it will be hold the information, so otherwise it lose, that is. So write operation in a dynamic random access memory cell to store a data. Row is opened, so that is a row line, word line opened, and given column sense amplifies it temporarily forced to the desired higher low voltage state. So column sense, that is a bit line, amplifies temporarily, thus causing that bit line to charge or discharge the cell storage capacitor to the desired value. So capacitor value will be maintained the desired value, then the charges will be hold. Due to the sense amplifier positive feedback, sense amplifier provide the feedback, that is a positive feedback configuration. It will hold a bit line at a stable voltage, that is a enough voltage will be maintained even after the forcing voltage is removed, right? So the essential voltage will be maintained, and it will be start losing. Before losing that, it has to be refreshed, that is, during a write to particular cell, all the columns in a row are sensed once, that is simultaneously, just as during reading. So just as during read operation, so this is once it will be sensed, that is okay. So although only a single column storage cell capacitor charges is changed, the entire row is refreshed, right? So single column storage cell capacitor charge is going to be changed, then the entire row is refreshed, that is. So coming to this discussion, we have what is called SRAM cell. We have seen that SRAM, we have that it is a contains of two transistors and the diodes, so that base is connected to the word line and other one side you connected to the bit line. So it will be maintain the status of the information into the cell depends upon the transistor conduction, not conduction, right? We have discussed enough about that. So this word line connected to the ground, and information will be, transistors are off, information will be stored. Now to drive out information, so supply some voltage to the bit line, then the cell will be activated either for read purpose or write purpose. So that mechanism will be exercised. So there is a n plus m number of address lines will be released from the processor. So since that matrix memory is a matrix fashion, so this given address will be split into row address and column address. So row address will go to the row decoder, that is 2 power n, and column address go to the write circuit along with that column decoder. So the entire information go to that memory cell. There is a chip selection, read, write bar signal will be there. So from this guidance, the information will be read or write action will be taken place. So this is a typical static random access memory cell we are going to be observe that. So similarly, the other simple mechanism with help of the single transistor and capacitor. So transistor base is connected to that word line, so this other side connected to the bit line, whereas the capacitor connected to ground, so it will be conduct. So this will be the faster slower access, but cheaper. The density of the memory cells is more compared to the SRAM. So this given address will be released by the processor. So n plus m address, so n for row, m for column. So the additional circuit is required. So because that capacitor is there, it will lose the information charges due to charges are loose and content of information is going to be loose. So that's why we need to be oftenly refresh. So for refresh, we need a refreshing circuit will be read, that will be connected to, that is a row address strobe. So the row address strobe connected to the one more circuit called refresh circuit. So that will be look after alternatively refreshing that. So that is a DRAM die compresses the multiple such arrays. So there is a 1 bit, 4 bit, 8 bit, so on, that data will be in or out possible. So the memory cell will be there to 2 power n row and 2 power m, those number of cells will be accommodated. We have seen so previous example, there is a 128 bit memory, 32 bit memory we constructed. So in similar case, this typical the circuit diagram for this both the SRAM and DRAM. So the as per the power concern about the static random access memory, the continuous power is essential, otherwise the data going to be loose, right? So that is a more power is a power supply is essential in case of static random access memory. So obviously less amount of memory is essential for DRAM, because that due to the capacitor it conduct and deconduct, so it holds some information, so certain amount of time, during that time we can interrupt the power, so no power, no problem. So that's why less power is essential. So density, number of memory cells will be lower in the case of SRAM, so that's why maybe cost maybe increases. So less number of cells will going to be formulated with help of this SRAM, whereas a high integration density, so large number of cells we can accommodate here, because only small circuit, that is a transistor, one transistor and capacitor. So the huge amount of memory cells may be possible to formulate here. The other area wise, the SRAM is a bigger size, the more area is required. So more area is required, the more power supply is required, more power supply and more cooling will be essential. So this is a very less area as we see in that. So the cost is a higher cost per bit in case of static random access memory, lesser cost for this dynamic random access memory. So refresh is not essential for SRAM. So it is a refresh is essential for dynamic random access memory, that is DRAM. So reading operation is very simple, whereas the longer access time is essential for reading with help of the DRAM. So from these points we are able to differentiate or discriminate this SRAM, DRAM, maybe power issues, maybe density of memory cells, maybe the size of the chip, and also cost. Additional SRAM that DRAM is refreshing circuit is required. The read and write approach simplification is we observed in SRAM, where the longer access time is essential for the DRAM. So this is a typical differentiation between the SRAM and DRAM, and we have seen that this discussion. So let we see general architecture of the memory organization. General architecture. So general architecture, so that memory basically it is formed in a matrix fashion. In order to locate the particular cell in a matrix fashion memory, so we need to be attack on the two sides. One is a row wise and other is a column wise. So the given CPU address generated by processor then we need to be split that address into row address and column address, right? So combining this address will be total address. So row address will be fed into the decoder, right? We have seen that to 3 to 8 decoder, 2 to 4 decoder, or 4 to 16 decoder, 5 to 32 decoder, so on that. So there is a decoder that is 2 power k minus j, that is number of address lines will be there, and it will be produced. Similarly, column address. So A0, A1. So we have the given lower bits will be lower LSB of bits of the processor address will be go for column, and higher the bits will be, that is MSB, goes to the row address. So that is a, we are observed there is a low column decoder. So it will be decode that column address, and this both row and column decodation, it reaches to the memory. So memory, we have cell, there is a several cells will be there, so that will be we can observe that is. So there is a bit line, that is a column lines we have observed, and there is a word line, row wise rows, row first, row second, so n rows are there. So there is a word lines are there. So we have that storage cell, that is we have storage cell, can observe, that is a random access memory or DRAM cell can be possible. So any memory concepts we can employ here. So to discuss this, so this is a complete typical memory organization for any computer. So there is a m into 2 power j number of data lines will be there, that decoding after column decoder, select the appropriate word from the memory row, amplify bit line swing, that is. So sensor amplified, reader write circuits, there is a input and output, m bits will be there, right? Input and output. So this will be input or output. We have seen a 1 bit, we have seen 4 bit, 8 bit, 16 bit data in and out, right? So this n number of bits, m bits will be there for input and output purpose. So from this complete discussion, we have learnt how to organize a memory, and how to locate the that cells, either SRAM or DRAM, right? So this complete discussion which help us to understand the more memory related concepts, so in the subsequent discussion. So from this, so I hope you are able to listen that, understand. Thank you for patient listening of the topic, the memory organization, the two static cell and dynamic memory cell. So and also their difference we observed, and the books are Kaur Hemachar, Ranchik, Sapwat, Jaki et al. Computer Organization, 5th edition, Tata McGrail, William Stalling. So that Pearson Education, Pearson, the 9th edition, Computer Organization and Architecture. There is also other reference book will be there. So thank you for patient listening once again. Thank you, coordinator, moderator, and the subject expert. Thank you, one and all.